All right, let's run through our Unit 2 mid-assessment review here. So on number 1, we want to expand this polynomial. So that means multiply it out. I'm going to start by just multiplying out these two binomials, 5x minus 1 times x plus 3. So I'm going to come off to the side here and set up my box to organize that. So 5x minus 1 times x plus 3. So 5x times x is 5x squared, x times negative 1, negative 1x, 5x times 3 would be 15x, and 3 times negative 1 is negative 3. Combine my like terms here, my 15x and my negative x, so I can say that this would become 5x squared, 15x plus negative 1x would be 14x, minus 3. Okay, so at this step, what we've determined is I can rewrite my original polynomial as negative 2 times, now we just multiplied these two together and got 5x squared plus 14x minus 3, and then we still have this x minus 7. So now I want to take this second degree polynomial and multiply it by my last factor. So I'll come over here and set up another box to organize that, this time a 3 by 2 box. So 5x squared, 14x, negative 3, times x minus 7. So x times 5x would be 5x to the third power. Then x times 14 would be 14x squared, x times negative 3, negative 3x. Negative 7 times 5 would be negative 35x squared. Negative 7 times 14 would be negative 98x. And negative 7 times negative 3 would be positive 21. So now I've got some other like terms to combine. No x cubes to combine, so that would just be 5x cubed. I can combine my x squareds here, so negative 35x squared plus 14x squared would be negative 21x squared. Negative 98x and negative 3x would combine to negative 101x, and then nothing to combine my 21 with. So at this step, we now have negative 2 times this polynomial down here, 5x to the third power minus 21x squared minus 101x plus 21. And finally, I can distribute my negative 2 through to all of these terms and expand this out to negative 10x to the third power plus 42x squared, negative times a negative would be a positive here, then negative 2 times negative 101x would be plus 202x, and then finally negative 2 times 21 would be negative 42. All right. Number 2 then. This one was kind of open-ended. There are a lot of possible correct answers for this one. So write at least 2 possible expressions in factored form that could represent f. Now, if I have an x-intercept at positive 6, remember the factor that would come from would be x minus 6, because we're thinking, okay, well, what happens when I set this factor equal to 0? If I set x minus 6 equal to 0 and solve, I would have to add the 6 over to get x equals positive 6. Okay, that's why the factor of x minus 6 is what yields an x-intercept of positive 6. Okay, so with that in mind, I can write the rest of these factors then. I could just say that this x-intercept of 3/4 could come from a factor of x minus 3/4. 0 could come from x minus 0. Negative 4 would come from x plus 4, and negative 8 over 5 could come from x plus 8 over 5. Now, this middle factor that I wrote of x minus 0, much more commonly, we will just see that written as x, all right, just as x. So I'm actually going to go ahead and change that here, and I'm going to make this factor just times x. Now, I mean, this could have any coefficient on it as well. I could write this as 5x or 37x, because again, what I'm thinking is what happens when I set that factor equal to 0. So if the factor is by itself just x and I set that equal to 0, I already have my answer of 0, or my x-intercept of 0. Let's say I made this like 2x instead. Well, if I set 2x equal to 0, to get x by itself here, I would have to divide by 2, and 0 divided by 2 is still 0. So this would still yield an x-intercept of 0. All right. So another common thing that shows up to get an x-intercept of 3/4, I could also write that factor as 4x minus 3. Okay, as 4x minus 3. And again, the reasoning there is if I think about setting that factor equal to 0 and solving for x, well, I would have to add the 3 over and then divide by 4. And we would get positive 3 over 4. Okay, so 4x minus 3 would also yield an x-intercept of 3/4. Then again, for my x-intercept of 0, I could write that several different ways. I could say that this is going to be negative 7x. Again, because this, if I set this equal to 0, I'm still going to get 0. And then similar to the 4x minus 3, I could write this factor as 5x plus 8. And again, if we just practice or set that equal to 0, we would see that we would get negative 8 over 5 as my x-intercept. So there were a ton of possible correct answers for this problem. Here are just a couple of them. For number 3, to find points of intersections, remember what we need to do is set my functions equal to each other. So I'm setting a of x equal to b of x. All right, so a of x is x plus 8 times x minus 2, and then b of x is x minus 2. Now, the way that we solved problems like this, we wanted to get everything on one side equal to 0. So I'm going to start by subtracting this x minus 2 over to the other side. Now, on the right side of my equation, something minus itself just equals 0. On the left side, though, these x minus 2's do not cancel because this x minus 2 is being multiplied by something else. So I'm just going to write my left side as x plus 8 times x minus 2 minus x minus 2. Now, at this step, we wanted to look for a greatest common factor. Both of my terms have an x minus 2 in them. So if I factor out my x minus 2 and then write everything that's left over in my second set of parentheses, I can take out that GCF. Now, what's left over will be after I take that x minus 2 out of each term, or in other words, divide each term by x minus 2. So in this first term, when I take out that x minus 2, right, what happens is x minus 2 over x minus 2 just equals 1. So x plus 8 times 1 is just equal to x plus 8. Well, over here, x minus 2 over x minus 2, again, just equals 1. So here, this part just becomes minus 1. So I need to include that in my set of parentheses here as well. So I can just combine my like terms here. X plus 8 minus 1 would just become x plus 7. And now I can set each of these factors equal to 0. Since I am to a point where I have two things being multiplied and set equal to 0, I can set them individually equal to 0. So for this first one, I would add the 2 over and get x equals positive 2. For my second one, I would subtract the 7 over and get x equals -7. So those are the x coordinates of my points of intersection. So far we've determined that one of the points of intersection is 2 something, and the other one is -7 something. I still need to get the y coordinates for each of those points. To do that, I'm just going to take each of these x coordinates and plug them back into either of my original equations. B will probably be easier, so I'm going to plug 2 in for B. So this would just become 2 minus 2, right? I'm just replacing the x with 2. 2 minus 2 is 0. So that tells me the y coordinate of this point of intersection was 0. So if I do the same thing for -7, and I plug -7 in here for x, well, -7 minus 2 gets me -9. So this y coordinate for this point of intersection is -9. Right? So if I were to graph these two functions, they would cross twice at the point 2, 0 and at the point -7, -9. All right, let's take a look at number 4. So this one, I want to find what coefficient I would have to put here if I know that x plus 5 is a factor. So, this should say what is the value of u, not k. All right, so I want to think about setting this up using synthetic division. So first of all, if x plus 5 is a factor, we have to think, well, what value of x is going to make this factor equal to 0? Well, subtract the 5 over, and we get -5. So -5 is the value that's going to go up in my box up here. Then I just need to list out the coefficients of my polynomial. So 1, 4, -u, -28, and 60. So if I start going through my synthetic division process, well, bring the 1 straight down, multiply 1 times -5, add straight down, so that would be -1, multiply, that would be 5. Now, we have two options here. I can continue this problem and just say that down here, this would then be -u plus 5. Or I can come over here and start working backwards. Now, if I know that x plus 5 is a factor, I know that my remainder would have to be 0. That means that this value in my synthetic division would have to be -60. Well, then I can just think, well, -5 times what would get me -60? So this value here would have to be 12. So then I'm thinking, okay, well, -28 plus what would get me 12? That would have to be 40. And then -5 times what gets me 40? Well, that would have to be -8. So to figure out what u is then, I can just look here in this little column, and I can create a small equation. This would just be -u plus 5 equals -8, and then I can solve this for u. So I can start by subtracting the 5 over, and I would get -u equals -13. So then technically I need to get rid of that negative sign and divide by -1. So I get that u would have to be 13. Now we could double check ourselves. I could set this synthetic division problem up again, replace my u with 13, and make sure that I do get 0 at the end. That would be a good way to double check yourself. All right, on number 5, I want to determine if x minus 1 is a factor of this polynomial. So I want to divide it out. Again, just like the last problem, I want to think what value of x will make this factor equal to 0. Well, +1. So that's the value I'm going to put up in my box, and then I'm going to list out my coefficients. So 1, -4, -7, and 10. And then if I go through my synthetic division process, bring that first number straight down, multiply, add, multiply, add, multiply, and add, and we get a remainder of 0. If we get a remainder of 0, that means that yes, x minus 1 is a factor. Okay, so I guess the answer to the first part of this problem is yes. So now we can go one step further and write g of x as a product of linear factors. Right? So what we've done so far, I am able to rewrite g of x as that factor that we just divided out, x minus 1, times what I have left over down here, my result. Now, since we started with a third degree polynomial and I divided out a linear factor, that means these are the coefficients then on a second degree polynomial. I'm just subtracting 1 from the exponent of what we started with. So this would be 1x squared minus 3x minus 10. So now I can go one step further and x factor this polynomial here. So if I come over here and set up my x, a times c would be 1 times negative 10, so negative 10, and then my b value is negative 3. So I'm looking for two numbers that multiply to negative 10 and add to negative 3. Well, that would have to be negative 5 and positive 2. Don't forget, at this step, we need to divide each of these values then by my a value. In this case, though, my a value is just 1, so that's not going to change either of these values. Negative 5 divided by 1 is still negative 5, and 2 divided by 1 is still 2. So that means that this second degree polynomial will factor into x minus 5 times x plus 2. So my final factored form would be x minus 1 times x minus 5 times x plus 2. Now we can use this information to sketch our graph. So let's start with our x-intercepts. To get our x-intercepts, I can look at each factor and think about setting it equal to 0. So for this first one, if I set x minus 1 equal to 0, I would just add the 1 over to get x by itself and get positive 1. Now, most of the time we don't have to write that out. We can do a lot of that in our head, right? So I know that positive 1 will be an x-intercept, and then here positive 5 will be an x-intercept as well, and then negative 2. So there are my 3 x-intercepts. My y-intercept, then remember, comes from the constant in standard form. That would be positive 10. So y-intercept there. And then the last thing we have to consider is our end behavior. That we will look at our leading term for. In this case, we have an odd degree, a third degree is odd, and then my leading coefficient is positive. So the end behaviors for that situation, for a positive leading coefficient and an odd degree, should look like this. So if I kind of connect all of that information, my graph will do something like this. All right. Now, number 6, the box problem. We spent a big chunk of the first part of this chapter talking about the box problem. So in this case, we've got a piece of paper that is 8 by 12, and I want to cut out squares from each corner, fold up the sides to create an open top box. So what we are saying is, each of these cutouts are x by x, and if the original lengths are 12 and 8, right, so the whole length was 12, and then I cut out an x by x square from this side and an x by x square from this side, the new length of this box would be 12 minus x, or 12 minus 2x. That's where this piece of information comes from. All right, so this is the height of my box times the width times the length. All right, but we are given that function. Now, for part A, to figure out a reasonable domain, right? Well, if x is the size of the cutouts, we're just kind of thinking, well, what is the biggest possible square that we can cut out from every corner? Well, the biggest possible square is just going to be half of whatever my shortest side is. So I can write my domain to say that x is going to have to be, well, bigger than 0, but smaller than, in this case, 4, because my shortest side is 8. So if I'm cutting out a square from each corner, I can't make a square that is more than half of the shortest side. So my domain is just going to be 0 to 4. Now, they give us the graph of this polynomial, right down here. On your paper, we have that graph. So we want to approximate the value of x that will give a box with the greatest volume. Well, I mean, that's going to be at that point right there. That shows me the greatest volume because we said our domain is only 0 to 4. So I'm only looking at this portion of the graph. I'm not looking at anything past 4. So, I mean, we can even kind of like scribble all that out, right? I'm not looking at any of this over here. I'm just looking at this portion of the graph that goes from 0 to 4. And we could even scribble out all the negative too. So, if I wanted to approximate that x value, well, I mean, it's in between 1 and 2. So I don't know, maybe slightly more than 1.5, maybe 1.6 or so would be the x value to approximate this situation. Now, part C then says, okay, well, let's find a much more accurate value. Let's use our graphing calculator to figure this out. So if I go to my graphing calculator, in y equals, I want to type in that function, right? So I'm going to go to y equals, and I already have the function typed in, x times 8 minus 2x times 12 minus 2x. We want to adjust our window then. So on our window, I've already made my x's go on the domain that we have already established. My x min is 0, my x max is 4. And then for the y's, we can start at 0, and then we may have to play a little bit with our y max. I just set it at 100. So if I go to the graph then, I want to check to see if this is a good picture, to see if I can see that maximum, and I can, right? The maximum is on the screen. So 100 was a good window to start with. To find that maximum value, I'm going to go to the Calc menu, so second, trace, and then the fourth option down is maximum. So hit enter on that, and it's going to ask me 3 questions. First, pick a point to the left, so I just want to move my cursor to where I am definitely on the left side of the maximum. Hit enter. Then it's going to ask me for a point to the right, so move my cursor to where I am definitely to the right, hit enter, and then it asks for a guess, so I can move my cursor back close to where I think that maximum is, hit enter one last time, and now this gives me my maximum value. So the x is the cut size, right? So my 1.5, if we round to the nearest hundredth, 1.57 would be the size of square I need to cut out, and then my max volume is the y value, so 67.60. So my cut size, 1.57, which yields a max volume of 67.60 in this case. Now, part D, for what values of x is the volume of the box increasing? Well, if I look at my graph here, I'm increasing from 0 up to where that maximum is. We just determined that that maximum was at 1.57. So, I mean, I could write this just to say x goes from 0 to 1.57. And I'm just seeing those are the values on my graph where I am increasing. And then finally, for part E, what do the points of intersection represent? Well, we graphed the horizontal line b of x equals 40. So what do those 2 points of intersection represent? Well, if my function represents the volume and I'm drawing a horizontal line at 40, those 2 points of intersection would just be the values where my volume of my box is 40. So I could have a cutout, somewhere between 0 and 1 here, that yields a volume of 40. And then I could have another sized cutout, maybe just slightly less than 3, that would also yield a volume of 40, right? So the answer to part E is just these points represent the values that would yield a volume of 40. All right, the last one, number 7. Let's sketch a graph here. So first, to determine the degree and leading coefficient, we theoretically would have to put this whole thing into standard form. So I would want to multiply 4x plus 5 times x minus 5, take that result times x plus 7, and then that result times x plus 7 again, and then multiply by negative 1/2. But if I only want a few pieces of information, I don't have to do all of that work. If I want my degree and leading coefficient, that's going to come from my leading term. Now, one thing that I do think is helpful is if we have a factor that is raised to a power, I think it is helpful to write out all of those factors like this. So if I've got x plus 7 to the second power, I'm just going to write that out twice. And the reason I think that is helpful is because if I want to find my leading term, well, I'm going to take any coefficient that's all the way out in front times every term that has an x. So negative 1/2 times 4x would be negative 2x, times x would be negative 2x squared, times x would be negative 2x to the third power, times x would be negative 2x to the fourth power. So that means that my degree would be 4, right? And again, if I'm thinking about writing this in terms of standard form, my leading term is negative 2x to the fourth power. So my leading coefficient is negative 2. Now, let me talk about what that means on the graph real quick. If I have a fourth degree, that's an even degree, and a negative leading coefficient, that means that my end behaviors will both be going down. Even degree, negative leading coefficient. So now let's talk about our x-intercepts. The x-intercepts come from setting each of my factors equal to 0. So my first one here, if I set 4x plus 5 equal to 0, remember that's not going to give me a 0 of negative 5. I would have to subtract the 5 over, but then I would also have to divide by 4. So we end up getting an x-intercept. I could leave it as negative 5 over 4, but to graph it, I'll go ahead and write that as a decimal. So negative 5 over 4 as a decimal is negative 1.25. Okay. Then I want to do the same thing with my other factors. Now these ones, again, we can write out x minus 5 equals 0, but these ones are a little bit easier to do in our head. This one would give me a 0 of positive 5, and then this one would give me a 0 of negative 7. Now, I do also have to consider the multiplicities of those zeros, how many times that shows up. So 4x plus 5 was just to the first power. So that means my multiplicity is just 1. That factor only shows up one time. My x minus 5 only shows up one time, but my x minus 7, or my x plus 7, shows up twice. Now what that means, remember, if I have an odd multiplicity, so 1 is an odd number, that means my graph is going to cross the x-axis at those values. But if I have an even multiplicity, my graph will bounce off the x-axis at that value. My y-intercept then is going to come from multiplying, again, any number out in front times all of my constants. So if I take negative 1/2 times 5 times negative 5 times 7, we get 612 0.5. So that would be my y-intercept. So I'll make that a mark up here, 612.5. Now, I guess to fill in my end behaviors, we already said they would both be going down. So that means both of these will be negative infinity. And then let's put our x-intercepts on the graph. So negative 1.25 would be right about there, negative 7, and positive 5. So if I now connect all of this information, let me scoot that over a little bit. We said we're going to be starting down. I will come up and go through negative 7. I'm crossing the x-axis. Then, oh, whoops, sorry, not crossing. I will be bouncing at negative 7. Let's try that again. Bouncing off the x-axis at negative 7. Then I'm going to come up and cross at negative 1.25. Hit my y-intercept of 612.5, and then come back down through at x equals 5. So this would be a decent sketch of my graph that shows all key pieces of information. Bounce at negative 7, go through negative 1.25, through my y-intercept of 612.5, and then cross at positive 5.